This is our video on force, momentum and time. It sort of fits in with our study of momentum, but as we look at generally in forces, this lesson links up a few ideas thinking about Newton's laws and really considers all of this in relation to the idea of impacts. And the impacts might be in a car, in sort of a car crash, but also safety of children's playgrounds or crash helmets. The physics is all the same. So we're going to look at an equation and then consider things like crumple zones, etc., as I say, in terms of car safety. So what do all these have in common? So we've got an airbag going off in some kind of a car safety test. We have sort of a gymnastics mat. We have a cyclist safety helmet, and then some safety flooring around a children's play area. Now, all of them are to do with impacts, and all of them are designed to reduce the effect of an impact. So rather than your head hitting a steering wheel, your head hits an airbag. Rather than your feet hitting a solid concrete floor, your feet hit a cushioned floor covering, a gym mat. Rather than your head hitting the floor if you fall off, your head hits the hat, which hits the floor, and your hat reduces the force of the impact. And if your little child falls off some children's play area, rather than hitting the solid floor, again they hit some kind of a cushioned surface. Now, why is this? And to really understand this, you've got to think about the ideas of velocity and acceleration and momentum and force and time. Okay, so the easiest way to consider this is what's going to hurt the most if you run into a brick wall or if you run into a haystack. And the idea is this: you can't just say the haystack's soft, so therefore it doesn't hurt. The idea you've got to have is this: if you run into a brick wall, you stop instantly. So you have momentum. When you hit the wall, you lose your momentum, or the momentum's transferred to the wall, but this happens very, very quickly. This happens instantly. If you run into the haystack, exactly the same things happens. You have momentum, but that momentum is transferred, but it's transferred over a longer period of time. So therefore you stop over a longer period of time. And what we can do, we can sort of plot this on a graph, and the graph we can use is like a force time graph. So this is the idea: to stop, you must lose or transfer all of your momentum, and the change or loss of momentum is equal to the product of the force times the time. So just thinking about this, if you need to lose or change your momentum, you can apply a very large force over a short time, or you can apply a small force over a larger time, and we can plot this on a graph to give you an idea of it. So for example, a 50 kilogram person moving at 20 meters per second, their momentum, mass times velocity, is 50 times 20, which is 1,000 kilogram meters per second, or newtons per second. And there's two options of losing your momentum. And the first option will be a large force acting for a short time. So here we need to lose 1,000 kilogram meters per second of momentum. So we can have a force of 10,000 newtons acting over a time of 0.1 seconds. And 0.1 times 10,000 will give us 1,000. Now this is a large force over a short time, and you could probably suffer serious injury, or as I've said, you could die if that force occurred on your body. Now the alternative is to have a small force acting for a longer time. And if we look at this graph, we've now got a force of just 1,000 newtons, so 10 times less force, but it's acting for 10 times the amount of time. So 1,000 times 1 second will still give us a change in momentum of 1,000 kilogram meters per second, or 1,000 newton seconds, but the force, as a smaller force, has occurred over a much longer time. So this is a far safer way to stop in the event of some kind of collision. So just kind of to confirm all this, when you stop, you lose or transfer all of your momentum. The change in momentum is equal to force times the time. So for the force to be as low as possible, the time needs to be as long as possible. Now, airbags, seatbelts, crumple zones are all designed to increase the time to stop, so decreasing the force. And again, another example, a driver has a mass of 60 kilograms and is moving at 10 meters per second. So her momentum is mass times velocity, 60 times 10, which is 600. Okay, so to stop in 0.1 seconds, the force on the person's body must be change in momentum divided by time. I've just rearranged the equation. So we'll do 600 divided by a time of 0.1 to give us a force of 6,000 newtons. Now, alternatively, to stop in 0.5 seconds, the force would this time only be 600 divided by 0.5, which gives us a force of just 1,200 newtons. So you can see this force has been divided by a factor of 5 if you have increased the time by a factor of 5. So how does this all fit in with the equation that's on the data sheet? This is what we've been working on. Force times time is equal to change in momentum. Well, where does it come from? Well, we can use these two equations, which we know about. Force equals mass times acceleration, and acceleration is change in velocity over time. You know those, you've got to learn them. If we combine them, we can have F equals m multiplied by delta V over t. So we end up as this equation, F equals m delta V over t. Now this equation's on the physics equation sheet, and m delta V is the change in momentum. So this whole equation becomes that the force is equal to the change in momentum divided by the time. Okay, and remember it is on the formula sheet, so you don't have to learn it, but you do have to know these two equations that I've used. Okay, some quick questions then. A ball undergoes a change in momentum of 22 kilogram meters per second in 1.2 seconds. What is the size of the force that caused this? Simply use the equation F equals delta, the change in momentum, 22 divided by 1.2, the time, that's 18.3 newtons. A force of 1.2 kilonewtons is applied to an object of 650 kilograms for 2 seconds. What is the object's change in velocity? So using our equation, F equals m change in V divided by t. Remember this change in is often called delta. So let's just rearrange it. Delta V, move the t up, bring the m down. So it's force times time divided by mass. So 1200. 1.2 kilonewtons is 1200 newtons, remember, times the time of 2 seconds divided by the mass of 650, and this gives us an answer of 3.7 meters per second. And then finally, a pellet of mass 8 grams is fired from a gun by a force of 250 newtons applied over a very short time, 25 milliseconds. What speed does the pellet leave the gun? Here's our formula, so let's have a look. Delta V equals Ft over m again. Let's put the data in. Force is 250 newtons. 25 milliseconds, remember, is 0.025 seconds. Need to make sure it's all in seconds. And 8 grams is 0.008 kilograms. Again, we've converted to kilograms. If we put all that in our calculator, we get a change in velocity of 781 meters per second. So hopefully you can see you need to be confident in your maths to rearrange this equation that you are given.